All right, let's get started. So thanks for logging on for today's webinar. We will be talking about white mica vectoring today and how to apply the mineral scalars to that application. So this webinar is going to have a little bit of everything in terms of how skilled you are with this application. So whether that be if you're someone who is brand new to the idea of using a field spectrometer and maybe you're interested in applying this specific skill set to your copper or gold porphyry deposit, or maybe you're familiar with the technology, have used it for white mica vectoring in the past, and maybe you're just here to brush up on the application. Now, for those experienced users who are here today and use this technology on a regular basis, there will also be some new information for you today as well. The outline for today's webinar will have us starting out giving a good educational overview of what the instruments do, how they apply to white micas, and why you would want to use white micas as a vectoring tool. We will also talk about other data sets that you can use with this technology, and we will go deep into this application of white mica vectoring in terms of copper and gold porphyry deposits. So we'll wrap up with a demo of our mineral scalars in our EasyID software as it pertains to this specific application. So the three field spectrometers that we offer are what we call the ORX Series. So these are built for the field, but can also be used in a lab or even a core shack setting, hence the portability aspect. So we've got the ORX Express, ORX Explorer, and ORX Expert. These field spectrometers differ in spectral resolution. The ORX Express is going to be a standard spectral resolution, meaning this is the industry standard that is accepted throughout the mining industry. It has a resolution of 2.8 in the ultraviolet, 8 nanometers in shortwave infrared, which we are going to refer to as SWIR 1, and 6 nanometer resolution, which we'll refer to as SWIR 2. The ORX Explorer is going to give you a little bit better spectral resolution than the ORX Express, and the ORX Expert is actually going to give you double the resolution than you'd get with the ORX Express. Now, spectral resolution matters in the mining industry due to the fact that you'll get more detail in your mineral spectra by having additional features that will not be present with your standard ORX Express. Now, if you're someone who just wants an instrument that has been around for a long time and just gets the job done, this is kind of what we would call old faithful. The ORX Express is for you. However, being a geologist in 2022, we all know that technology is getting better in all aspects of the scientific world. So that being said, it's going to be in your best interest moving forward to adopt the higher resolution instruments, just because that's the path that the world is moving towards, and you're going to want high resolution to match your other data sets from other types of instruments. So that's why something like the ORX Explorer will eventually become the new standard. So the ORX Expert is actually the highest spectral resolution on the market, and additional features in your alteration minerals will be of benefit to you, especially in the exploration phase. So for those new to the technology, in the previous slide, I was talking about the ultraviolet and the shortwave infrared regions. So our field spectrometers are what we call full range, so from 350 to 2500 nanometers. So we cover the ultraviolet, the visible, near, and shortwave infrared. Depending on your application, you may use spectral features of minerals that are present in other regions other than the shortwave. So when focusing on white micas in particular, we will focus on the shortwave regions only. So you will hear this referred to as SWIR throughout this webinar. The reason that we focus on SWIR and white micas is because the ALOH feature occurs at 2200 nanometers. Other important features are the MGOH feature at 2340 and the FeOH feature at 2260. So again, this is why we're going to focus on SWIR today. Okay, so many of you working on porphyry deposits, you're probably using other data sets from various other types of technology. Now, the beauty of using a field portable spectrometer is that the data is very complementary and can be used as a validation tool as well. For example, say you're doing some airborne surveys to get an idea of your mineralogy of a key area of interest. You'd want to somehow verify that information. So you do that with a field spectrometer using an approach called ground truthing to verify what you're seeing. Now, our data is going to be in ASCII format. So that means that you can upload this spectral data into any third-party software, such as Envy, for example, without the hassle of dealing with data conversion and that big headache. So our data is very easy to acquire. It's point-based, meaning you're in contact with the sample, and it takes about 3 seconds to take a measurement. It's non-destructive, so you don't need to prepare any of your samples unlike you would with XRD, for example. So why do we care about white micas and why are they important? So you can actually use the presence of white micas to vector in and around copper and other porphyry deposits, for example. So this is done by systematically identifying those certain alterations in a mineral system and examining the changes in mineral chemistry of the white micas, which will then lead you to that zonation that you're looking for. So the most use cases in the mining industry, they're going to require, acquiring large spatially constrained data sets. So this is why using a field spectrometer is an easy approach because it's fast and it's low cost. And again, to reiterate, it works well with other data sets such as geochemical surveys. So geologists particularly focus on alteration mineral assemblages that define basic alteration patterns like argillic, phyllic, potassic, etc. Now, certain mineral classes, including both mineralogical and textural, demonstrate more marked variability with respect to these changing conditions of formation, like temperature, pressure, and fluid chemistry. These minerals become reliable indicators of formation conditions and thus alteration zonation proxies. So one of the most prominent indicator minerals in this category are the white micas, but also more iron and magnesium micas like the chlorites and the phlogipites, for example. While various species of mica are found in most styles of ore deposit, copper porphyry is arguably one of the most important ones. So the presence of white mica can reveal both primary mineral formation conditions like igneous or metamorphic events, or can map out secondary alteration processes such as pervasive phyllic alteration, overprinting, or those vein-veinlet events. So the chemistry of these micas, as well as relative crystallinity, allows for the demarcation of these alteration zones that are used in exploration, drill targeting, and even environmental planning. So tracking white mica chemistry is used as a proxy for temperature, pressure, and characterization of hydrothermal fluids with respect to that mineralization potential. So these measurements are, again, they're both taken in the field or the lab settings. And so they're used consistently and accurately to identify those vast suites of minerals, whether that be, just using on hand samples or if you're in the field and you're wanting to map through entire districts. So these white micas are found in most style of ore deposits. Again, copper porphyry being one of the most important ones. So this is why you would want to use one of the ORX series field spectrometers for this application to give you a significant insight to your mica chemistry. You're going to do this by identifying and mapping a suite of those typical porphyry alteration minerals. This will allow you to then go in and create a mineral map that actually tracks those mica species, the chemistry, and the crystallinity. This information will reveal potential paragenetic relationships and indicator minerals that are going to be associated with that mineralization. So the white mica species that we will focus on today are paragonite, which is going to be an aluminum-rich mica. It has a distinct feature between 2180 and 2195 nanometers. Muscovite, which is at 2195 to 2215 nanometers, and phengite, which is aluminum poor and iron rich. And so it's going to have features between 2215 and 2225 nanometers. All right, so here's a plot of each white mica zoomed in on that 2200 nanometer region. So the red line you see is going to be paragonite, blue is muscovite, and green is phengite. Now, with respect to white micas, distinctive changes in the architecture of the spectral signatures are going to reveal this shift from more aluminum-rich paragenetic white micas, with the key absorption feature here located at 2190 nanometers, into muscovite, which is centered at 2203 nanometers, and finally terminating into that aluminum poor, iron rich phengitic mica centered at 2216 nanometers. In addition, the overall shape here and total depth of the white mica absorption features, they're located in, the approximate wavelength range centered on the 2200 nanometer. These are going to relate to relative crystallinity. So, as your ore zone is going to be approached, your white micas are going to start to become more iron and magnesium rich. So this is going to result in that shift from your aluminum-rich paragonite into your magnesium-rich muscovite, and finally into your iron-rich phengite. So using this in particular is going to help you grade towards, your more mineralized rock. So you kind of have to imagine in this picture up here in the top right corner, say you're scanning your core, right? So you would pay attention to this white mica shift as you're going down your core. And so as you, start to see that change into that more iron-rich phengite, that's going to help you, get towards your more mineralized zone there. If you'd like a good paper to read, Hallie and Dillis have a great paper here, quoted here, talking about the vectoring with the 2200 nanometer white mica shift. Now, the significance of this for vectoring is that the acidity of the fluids is actually a function of distance from the source, and hence a vector. So in other words, as the 2200 nanometer wavelength decreases, the conditions of... So here is a great diagram from that same Hallie and Dillis paper that shows a typical copper porphyry deposit and how the white mica 2200 nanometer shifts as you get closer to the zonation. So in general, as the ore zone is approached, these white micas will become more iron and magnesium rich, dropping the aluminum as the process progresses. So the result is going to be a shift from that aluminum-rich paragonite into a magnesium-rich muscovite, and finally into that iron-rich phengitic mica, which is grading towards and directly adjacent to that more mineralized rock. A similar process, which we see in this diagram as well, is going to be the other two mica species, the chlorite, phlogotite, biotite, where the iron cation is actually going to be substituting for the magnesium cation, which is going to result in the spectral shifts seen in the extracted spectral signatures. So mineral species can be used to partially track the fate of the iron, the magnesium, and the aluminum within this ore deposit system. Now, this is all due to what we call the Chermax substitution. I'll go over the Chermax substitution here in just a minute. If you would like to read some really great white mica paper resources, on our website, we do have a lot of papers and presentations if you want to check that out. There's a tab called Resources. But I do want to point out two really great papers that I find very useful. Again, the Halley and Dillis paper that I actually showed you diagrams from. That's a great one. And then also my friend Jonathan Huntington over in Australia, he does a lot of SWIR work on chlorites and white micas. So if you are interested in reading some papers, I highly recommend these. So back to the Chermax substitution. Now, this is going to be a phenomenon where the iron and magnesium can substitute into the crystallographic structure along with the substitution of those tetrahedral coordinated aluminum for silica. Now, in metamorphic rocks, this can actually be a function of metamorphic grade. And in hydrothermally altered rocks, this can be a function of temperature and pH at the time of formation, which is actually systematically zoned with regard to the hydrothermal center. So this exchange can be qualified by examining the shifts in that wavelength of the ALOH feature at 2200 nanometers. The textures, particularly veined versus pervasive of micas, may also help determine deposit scale paragenetic relationships. So these white micas, in particular the phengites, they're going to be more veined, while the paragenetic micas are going to be seen further from the mineralized zones and more pervasive in character. Now, the same relationship exists with the chlorites and the phlogopite, for example. So chlorite appears to both pervasively and as veins in the porphyry zones, and with the more iron-rich series expressed predominantly in those veins. So along with the predominance of iron-rich phengites, the concurrence of these iron-rich chlorites with respect to increased copper grade may also lend itself to future use of these assemblages as copper vector in, porphyry prospects. All right, so let's move over to our EasyID mineral identification software with mineral scalars so that we can see how those work with our specific application. Okay, so what you're seeing here is our EasyID mineral identification software. It's got some built-in mineral scalars over here to the right, if you see my mouse. So one of the most used scalar, especially for white micas that we're going to use, is this ALOH scalar. So this is going to tell us the wavelength value where the ALOH feature is going to be centered at. So remember we talked about how the spectral shift goes from the paragonite into the magnesium-rich muscovite and then finally into the iron-rich phenigite. So we're going to take a look at that. So I'm going to start out with paragonite. So if I zoom in here, this feature right here, or ALOH feature, if you actually look at the ALOH scalar, it's telling us that our feature is centered at 2191.7. If you remember, the wavelength range of these paragonites are going to be from 2180 to 2195 nanometers. So as I go through these three types of muscovites, I want you to pay attention how this feature here is going to shift to the right. Another thing that you want to keep in mind is as we are going from an aluminum-rich mica into a magnesium-rich muscovite, and then finally adding in, iron-rich phengite in there, you're also going to see this feature here change in shape. And that's going to be due to the increased magnesium oxide and also the iron oxide as well. All right, so let's move to the magnesium-rich muscovite. So again, pay attention to the shift. So you can see you've got a little bit of a shift to the right. So if I look at the ALOH feature, I'm now centered at 2202.5. And I've also got this little feature here that's shown up right here. That's going to be due to the MGOH. So if you see here MGOH, the scalar, very similar to the ALOH scalar in the sense it's going to tell you where my MGOH is going to be centered at. So at 2346, I now have a, magnesium feature there as well. Now let's move on to that iron-rich phengite. So again, we have another shift to the right. The ALOH scalar is now telling us that my feature is centered at 2219.7. But the interesting thing here is, remember, phengites are going to be more iron-rich. So we now have an FeOH scalar showing up. So at 2253 nanometers, we now have FeOH showing up. So you can use these mineral scalars here to not only track the spectral shift of your white mica going from paragonite into a phengite, but you can also track the presence of MGOH and FeOH. For example, as you're measuring your core, as you're going down your core, this is very helpful here. So we can physically see, the spectral shift. We can also see these, inclusions of the FeOH and MGOH. And very similar with the chlorites. So if you're also focused on chlorites, you can use the MGOH and FeOH feature for those as well. So let's go back to the webinar. So to conclude this webinar, you can see that using one of the ORX Series field spectrometers that we offer can help you identify your zonation a lot quicker by identifying that white mica shift and easily distinguishing the paragonite from that muscovite and then finally into the phengite. So this is done quicker and easier by utilizing those built-in mineral scalars in EasyID to better understand your deposit.